Okay, welcome back. Let's continue our discussion about magnetized plasma. The second part will start from page 36 to page 53. But this time we will focus on the physics itself. I will introduce many kinds of modes, including electrostatic mode and EM waves in different frequency range. Okay, so first, let's consider wave number propagating in a direction the same as the B0. That is, like this case, B0 in a Z direction and K also in a Z direction. So perpendicular component will be 0. Perpendicular component will be 0. For a small argument, the Bessel function, the argument is very small. Argument x very small. And we can write into this form. And okay. Next slide. For the small argument of Bessel function, this one, we found that the perpendicular component, so luckily, other components are zeros. These 4 are zeros. So we still have 5. 1, 2, 3, 4, 5, just like this one. These 2 and these 2 are 0. So the determinant equals 0, which means this one is 0. We can rewrite into this form because xy equals y minus ys. So it's a plus here. Okay, next slide. These equations give us that the determinant tells us that dzz times this one equals 0. So several modes are contained in this equation, several modes. To find these modes, we assume that the plasma is isotropic in 3 directions. In all 3 directions, okay? That's the simplest case. Isotropic in all 3 directions. Of course, later on, we will change the assumption. Here is isotropic, isotropic in 3 dimensions, S, Y, Z, the same. Okay. But remember, in the previous case, we say we can divide it into V perpendicular and VZ, 2 directions. This is X, Y, and Z. Okay, so let's consider the simplest case. That is electrostatic case. DZZ equals 0. This one equals 0. O, this one equals 0. One of the solution, which is this one, which by equation 180 can be written as this form. O, this form. Here, G alpha 0 is shown here. Okay, move on. In other words, that's the integration. Equation 190. Equation 190 is shown here. The integration tells us that we have a singularity here. And we can rewrite this integration into this form. kz. Okay, so we integration by part. Integration by parts. dz. Sorry, we have integrating by parts. Okay, and the other one is this one. Okay, that's integration by parts. So this integration by parts. Okay, so eventually we obtain an equation we're familiar with. We spend a lot of time electrostatic EM wave, which agree with electrostatic dispersion relation we find in equation 135 from unmagnetized plasma. This is because electrostatic wave involve particle motion along B0, hence are unaffected by the magnetic field, which means the particle move in Z direction. Therefore, no effect at all. Okay, so just imagine electrostatic plasma oscillations. Yeah, so unaffected by the magnetic field in the Z direction. And that's why it's independent of the direction, it's isotropic. Isotropic, that's why. Okay, another case, homogeneous wave. Electromagnetic wave. Electromagnetic waves. And once again, we have these two conditions, these two solutions, in addition to this one. This one gives us electrostatic, and these two give us a new information. We recall the dispersion relation D determinant equals 0 is based on the condition for solvable wave equation. For perpendicular, we say these two equals 0, dxs equals dyy. And so we can simplify into these two. That means ex and ey will be differ by not exactly. Es is related to ey. Ex is related to ey. They have a ratio here, shown here. Two conditions. The first condition, the second condition. Okay. So let's rewrite these two equations. We have two conditions. The following information about the modes can be immediately learned from equation 196. 1. The two equations here are consistent only when this one. Yeah, because this one plus this one plus this one equals 0, right? So this is a specific example which shows that the dispersion relation at the condition for solvable of the field equation gives the relative amplitude. The amplitude will be the same. A typical linear solutions. 2. The field 196 are in the SY plane with K propagating in the Z directions, and E is here. So divergence E equals 0. The two solutions represent electromagnetic waves. Two solutions here represents electromagnetic wave, EM wave. Okay. Either the equation gives this one. Hence, we have a simple relations. One is these conditions. The other is these conditions. E1k S component minus IEY EX plus IEY. So both waves are circularly polarized waves. Without loss of generality, will explain later. We assume a positive omega 0. Omega 0 is normally positive. Omega B0 is the magnetic field. At any fixed position Z, the field in equation 198 rotate opposite to the gyration of electrons in B0. So let's X direction, Y. So obviously G will be pointing out, pointing outside this plane. Okay, SYG. So use your left hand. This is left hand circularly polarized because the wave is propagating in a Z direction. So you are looking at the wave rotating left hand circularly polarized. On the other hand, that's truly on the other hand, the wave propagated to you, and your thumb point the wave propagation, and so this is right hand circularly polarized. Once again, this one, right hand circularly polarized, left hand circularly polarized looks like here. Right hand circularly polarized in this case. Okay. So turning to the dispersion relations, we have dSS minus IDY. dSS minus IDY, this case, we have these relations. Similarly, DSY, DXS plus IDXY, we have another case. Quite similar, right? Quite similar. Okay. Using equation 180. What is equation 180 and 182? Go back to equation 180. That's the equation 180. So equation 180. Okay. We can rewrite the left-hand circular polarized into this form. Minus. And right-hand circularly polarized into this form. So right hand is plus, left hand is minus. Left hand, right hand. Okay, these two dispersion relations in their present forms allow an isotropic F alpha 0, which may lead to instability. We will provide at the end of these sections. For an isotropic plasma, we have this one. This one, we have isotropic plasma. These two are equivalent. For an anisotropic plasma, then we can reduce, for an isotropic plasma, it can be reduced to this form. That's left-hand circularly polarized. That's right-hand circularly polarized. Integrating by parts with respect to B perpendicular. Integration by parts. eventually we got these terms. We got these terms. Okay. We got this term for the left hand. For the left hand, we have this one. For the right hand, we have another one. Okay. Quite similar to the equation we found before. Omega squared minus kz c squared minus this one. The major difference is here, because of magnetic field, because of B0 in the z direction. Okay, and remember, K is Kz, Ez, the same, in the z direction only. The best property of the wave can be most clearly seen in the core plasma. So the core plasma is no temperature distribution, no thermal distribution. So no thermal distribution. We just assume this one here is delta function centered at 0, like freeze. Okay, so the velocity distribution function tells us that it's 1. Therefore, these two equations reduce to these two cases. These two cases. Okay, these two cases. Right circularly polarized, left circularly polarized. The simple equation. And alpha here just represent electron or ion. If you have more than one ion, if you have a positive ion, you have negative ion. So we sum over all alpha. As an exercise in the kinetic treatment of plasma wave, we have gone through great lengths to arrive at the above dispersion relations for cold plasma. In fact, equation 209 and 210 can be readily derived from the fluid equation. You can check Nicholson or Curl and Trail-Peace. Curl and the Trail-Peace. Nicholson, Curl and Trail-Peace. Okay. Assume the plasma contains only one ion species, just one, not two, and one ion species. The ion species charge E and mass Mi. In all the equation, okay, that's different by this charge E carry a sign of Q alpha. The mass is M alpha. To be more expressively, we define omega E, that's the cyclotron frequency of electron. That's the cyclotron frequency of ion. But this case, Q alpha equals E. Okay, so we have something in common. We have two cyclotron frequency. One is omega E, the other is omega I, 2, omega E and omega I. Then equation 209 and 210 can be written. That's the from electron, from ion, electron, ion. They differ by a minus sign. Okay, so this is left-hand circularly polarized. This is right-hand circularly polarized. Each equation can be put in the form of a fourth order polynomial in W, because we have omega, we times omega squared is a fourth order polynomial. fourth order polynomial, polynomial, fourth order polynomial in omega. So for a given kz, there are four solutions of omega. Okay, for 1 kz, we have 4 omega. Okay, however, with omega change to minus omega, change to minus omega, one equation becomes the other equation. They're different by a minus sign, which means a negative omega solution of one equation is identical to the positive omega solution for. So there must be 2 positive omega I, 2 negative omega I, 2 negative omega solutions for each equation. That results in a total of 4 independent solutions. This results in a total of 4 independent solutions. Okay, and also tell us if we change omega, yeah, a negative omega will still have the same solutions. A negative omega change to omega, this one will change to this one. This one change to this one, and this equation change to this one. Okay. Furthermore, with a change of the sign of B0, the 4 equation also reversed. Okay, so go back to this one. When we change the magnetic field from positive to negative, just means in a positive EZ to in a negative EZ. B0 EZ. Okay, B0 can be in a Z direction or minus or negative Z direction. So it's okay. So when we change the sign of B0, that's the magnetic field, the 2 equations are also reversed. So without loss of generality, we may restrict our discussion to a positive omega solution for a positive B0. Okay, because positive and negative B0 and they have something in common. 4 independent omega, 4 independent positive omega solutions of these 2 equations are in positive B0 are shown in figure 1 or figure 2 in 4 branches. That's the branch 1, second branch, third branch, fourth branch, ranging from very low to very high frequency. Various waves in these branches will be classified below according to their frequency range. According to their frequency range, okay. So although it's still chapter 6, but it covers Nicholson chapter 7 already. Okay. So this is omega. We have omega, and this is kz. So this one is the so-called omega kz relation. That's the dispersion relations. Okay. Omega E is the cyclotron frequency. Omega I is the cyclotron frequency for the ion. And another example, omega E is here, omega I is here. Omega E is somewhere between these 2 solutions. I will show you quickly. So let's focus on maybe here, these 2 cases. A, high frequency electromagnetic waves. high frequency electromagnetic wave here, high frequency EM wave. We have an effect called Faraday rotation, 法拉第旋转, just like ferrite material. Ferrite material. For high frequency wave, the ion turns, and so we have for high frequency terms, high frequency, omega is much, much higher than omega I. So in principle, let's focus on here, these two. Omega is greater than omega I. The ion turns can be neglected. So we have these equations only, simple equation. The high frequency branches are plotted in the top of the two curves in figures 1 and figures 2. These two, this curve. So we have two conditions. We will classify into two conditions, two categories. Okay, setting Kz equals 0, we find the cutoff frequency of the two branches. We have two roots. Under this condition, Kz equals 0. Kz equals 0. Go back to this one. Kz equals 0. Kz equals 0. We have cancel. So we have omega times omega plus omega E. Okay, omega times omega minus, yeah, they can be that's second order polynomial. So two roots, okay, two solutions, minus plus omega E. Okay, the two figures differ in the plasma frequency. If omega PE is greater than this one, so what will happen? Omega plasma frequency is greater than here. We have omega 1 will be greater than omega E, just like this one. Omega 1 will be greater than omega E. When omega PE less than 2 square root, we have another conditions. So these two figures differ in here. That's the plasma frequency is greater than the sectron frequency. We have these relations. When the plasma frequency is less than square root of the sectron frequency, we have another equations. Okay, of course, when B0 equals 0, there's no sectron frequency. Two branches coalesce with the same cutoff frequency, omega E. That means without magnetic field, these two will be the same. That's the EM wave, simplest case. Nope, we don't have to worry too much. That's the plasma frequency. So with the same cutoff frequency and the same dispersion relations. So it's something looks very similar to a waveguide. This plays a role very similar to the cutoff frequency of a waveguide. For cutoff frequency of a waveguide. So its behavior quite similar to a waveguide. So without magnetic field, unmagnetized plasma, very similar. Now, as shown in figures 1 and 2, at a given frequency, the right circularly polarized wave have a greater phase velocity Let's go back to this figure again. At a given frequency, this one, frequency the same, but kz is different. So phase velocity is kz. Therefore, right-hand circular velocity, phase velocity is greater than the left hand. This is Vp. Obviously, the right-hand circularly polarized wave has higher phase velocity than the left hand. The right circularly polarized has a greater phase velocity than the left circularly polarized wave. Hence, if a linearly polarized wave, if we have inject a linearly polarized wave into the plasma, it may a linearly polarized wave to the plasma, it oscillates in this direction, just like one left hand, the other right hand circularly polarized wave. Okay, a linear can be decomposed into a right hand circularly polarized and left hand circularly polarized, and of the equal amplitude. Each travel at a different phase velocity. Right hand is faster, and left hand is lower. The combination wave will still be a linear polarized wave, but they will change their polarization. After it propagates inside the material, one will change, will differ by a different angle. So looks like the polarization will change from initial polarization to another polarization. Okay, so initially in this direction, we can control the length. So KZL, right-hand circularly polarized and left-hand circularly polarized, will differ in a phase angle. So it looks like the polarization will rotate. Therefore, we call this phenomena as Faraday rotation. Faraday rotation, and is exploited for plasma density measurement. So you can detect the plasma density through the change of the angle. So this is a very useful technique. Okay, so incident wave may be in this direction. As it propagates, it might change to these directions, and they will be related to the plasma frequency. Okay, so we can control the frequency, we can control the polarization, so we can detect the change of the polarization. Then we can determine the plasma density, the most important plasma density. In an unpolarized plasma, there is no electromagnetic wave below the cutoff frequency. Okay, a magnetized plasma, however, can support other branches of EM wave. A surprise at frequency below the cutoff frequency. Without magnetic field, we say the cutoff frequency should be here. But with magnetic field, we can generate another branches. Go back to this one. Another branches, and which will be lower than the plasma frequency, or lower than the spectrum frequency. Okay, that's very interesting. So we provide another routes to generate the wave less than the plasma frequency. Interesting, surprise. Second, intermediate frequency of EM wave. Intermediate 中间的 frequency. Whistle wave, whistler wave, or electrostatic wave here. Whistler or electrostatic wave. Okay, that's another case. In the intermediate frequency range, we still have omega greater than omega I. That's always still apply. Equation 213 has no other solution in this range, and equation 214 has a solution marks Whistler and electron sectron wave. Whistler here, electron sectron wave here. Whistler, electron sectron wave. The electron sectron wave can be exploited for the electron sectron resonance heating, since it has been the same frequency as the electron sectron frequency, and it rotates in the same sense as the electrons. Rotates in the same sense as the electron, so it's related to electron. Related to electron. How about Whistler? For a Whistler wave, a group velocity, Whistler wave, group velocity increase as omega increase. The phase velocity here in these regions. Whistler wave. That means Vg is proportional to omega. What is Vg? Vg is the omega over the kz. That's the group velocity. Okay, so a lightning 闪电 stroke on Earth generate a pulse of EM wave containing many frequencies. Lightning strike on the ground, on Earth's atmosphere, on the ground. Lightning strike on ground. It generates a delta function. So it consists of many frequencies, very broadband. And the pulse, this is the Earth's ionosphere, lightning here, and generate a wave, generate a broadband signal. So the wave will reach the ionosphere, 电离层或是游离层 and propagate along the magnetic field, 然后会随着地球的磁场 as a Whistler wave. 为什么叫 Whistler? So the wave will eventually leave the ionosphere to impinge on Earth. 撞到地球上，再反弹回来地球上 where it can be received via radio to generate a sound like a whistle. 低频率的传得比较慢，高频率的走得比较快。Hence the wave， 那听到了就会变得好像本来是一个很delta function的，就会被拉长，所以就很像是一个 Whistler wave。Something like that. The radio signal has a duration longer, 所以它持续的时间范围，因为波长被拉长了。Because the component at different frequencies travel at different group velocity in the ionosphere. 所以在有闪电的时候，我们会听到有点类似吹哨子的声音。如果有闪电的话，在比较远的地方，然后这个 signal 会沿着 ionosphere， 会沿着我们地球的磁场这样传递，因为它是记得吗？ 我们现在假设是 z direction， 然后磁场也在 z direction， 所以它会产生一个 z direction 的 wave， 这个叫做 Whistler wave。然后当 kz 变大之后呢，当 kz 变大之后，这个的重要性就不是那么大了，就更重要的是 electron sectron frequency omega 1 eventually 就会变成这个频率了，会 saturate。OK， 我们还有另外一个 orphan wave and ion sectron wave， 这是我们下次 we will discuss orphan wave, ion sectron wave next time. Okay, this is the end of today's course. See you next time. Bye bye.